最近上课上的非常频繁，大家可能要注意消化一下。你上节课可能有的同学不在，我们上节课的内容我完全可以用。So last lecture we talked the path integral from the quantum physics. Essentially, we do analysis of quantum mechanics. Okay? So we explain the quantum mechanics. The transition amplitude can be right as the quantum right of quantum. This one we should prove. Okay. Now, similarly, your quantum field theory, similar to this one, quantum field theory. Yeah, one can try to translate this amplitude from initial time in vacuum state and to the final time of the vacuum state. And we realize that it's nothing that this field passing through. So if this is vacuum state, we didn't quite specify the boundary conditions. So if this is some explicit initial and final state in quantum mechanics case, we specify boundary conditions. X and T equals X and T X up. Okay. So this is what we can derive. And what's the point? The purpose to do this is very convenient to calculate the coefficient function. So one can further talk about what happens if there are some insertions here. Okay, if I try to insert a field inside this path integral, okay, I put something here. Then what is the meaning of this? Okay, what is the meaning of this object? So the key observation is for these insertions, automatically inside the path integral, the meaning of this kind of thing encoded in operator language, the time ordered operator insertion for this for the operator corresponding to this field. Okay, like that. Now I can easily check, right? Let's go back. You go back. In order to understand this one, you go back to the canonical formalism. Do you ask which operator does the job to create such kind of insertion in the path integral? Then you realize that it must be some operator. It must be some operator at some particular time. Okay, at some particular time. Depends on which time the insertion is here. Okay. Because in the canonical formalism, canonical quantization of operator language, we always evolve from right to left, and the earlier time should be always on the right, and the late time should be always on the left. Okay, so the time order is guaranteed, or it's automatic. If you want to understand this path integral, okay, this is very, very important. Very, very important. So therefore, one can use such kind of expression to express the endpoint correlation function, and so this is nothing but the time order correlation function. Okay, not time order in this case 2-point function. And you push this, then you get the endpoint time order endpoint functions, right? Then we also discussed there is a powerful trick called the generating function trick. Generating function trick. So this is it. One can try to improve the action to some plus some integral j by coupled term. Okay. Basically, the j means false. So we improve the action into this one, put it in the path integral, and then you get the generating function. And you can immediately work out. There's a beautiful relation between the derivative of variation with respect to the j. This is directly connected to the endpoint functions. Okay. No matter this is a Frey theory or interaction theory. We found a trick. to calculate this one, basically, okay? So in path integral language, the only thing you have to calculate is this one. If you calculate this one, then we get the endpoint functions. And we checked some examples. Okay? We checked the examples of free theory and also interacting theory. Indeed, we see it produced the normal result. Okay? So we believe this trick is correct, also powerful. And as you can see, this also can reproduce all the Feynman rules. Okay. They reproduce all the diagrams, okay, all the structures, and you can turn to the graph picture. Then you say, okay, this is nothing but what we derived using some other method before. So this is the power of the path integral. So do you have any question about this? Do you have any question about what we learned last time? Yeah, since we only have now two for lectures, including today, maybe after today we only have one lecture. So we want to use the remaining two lectures to discuss new topics, okay, in quantum field theory, which is subtle and yeah, it needs to be explained rather than just a direct calculation, follow direct calculation. Okay. So now we switch to some new topic. New topic today, something called renormalization. Okay. Renormalization. Wow, renormalization. The name is not that good. You know, we know what is normalization, right? What is normalization? Okay. Then renormalization means what? No, that's not a good enough translation, right? They cannot just translate it in a straightforward way. So in Chinese, it's translated 重整方. We'll see why. So renormalization is more subtle than normalization, okay? So people invented this word just to deal with in history or in early stage of the development of quantum field theory. You just want to deal with something divergent, okay? Mathematical divergence. Okay. The point is, when you by straightforward calculation in quantum field theory, sometimes you just get something divergent. Okay. Then we know in our real world there's nothing is divergent. Okay. There's no divergent physical quantities. Okay. Okay. So we don't know how to, in the beginning we don't know how to understand this this beast. Yeah, we don't know how to deal with this. People invented a program to deal with this. Yeah. To deal with this doesn't mean we really understand this divergence itself. Okay. We somehow just get around it. We split the prediction and the mathematical completeness. We treat these are not the same thing. Okay, even though the theory may carry some, normally may carry some mathematical divergence, but still it has power of prediction. Okay, it doesn't mean it's bad. Okay, we can just use it, and by some trick, you will say, okay, the theory still can predict very well. Okay, and try to compare with experiments. That's what we want. So our current knowledge don't have a full, complete understanding of this divergence. Okay, but we extract the prediction power of the theory. Okay, which seems disregard of this divergence. Okay, so that kind of idea of program named renormalization. But divergence is not something really new, right? We already saw it somewhere, right? Do you remember? We already saw this divergence in the very beginning, right? In the very beginning, when we quantize the free theory, you remember that?
Vacuum energy.
That's right. When we calculate the vacuum energy, eventually, well, there's a sum. You see, you still remember the sum of the moles, right? The moles, the omegas. Then that sum is not convergent. It's a divergent. There is a divergence there. So it's not something really new. But what's the point? So see, we already saw the divergence. By computing vacuum energy. Or ground state energy, okay? But we didn't worry too much about this divergence, right? Why? Because quite often we don't observe the ground state energy itself, right? We don't observe that energy itself. Quite often we only care about the relative. I make a reference energy level, then I measure all the other energy levels. What is the relative difference between these reference energy level, right? And so the point is, so vacuum energy E is not observable. It's not observable. Okay. It's not observable. We cannot directly observe this. Okay. And a related quantity is the cosmic energy. Okay. Maybe you learned something from your other course, electrodynamics. You learn something about cosmic energy. It's very similar, right? So what is the cosmic energy? We have two planes, okay? You have two planes, okay? And then you can calculate the energy, okay? Then you can calculate the energy. Then there is an amount of energy, okay? Because you have two planes. There's a finite scale, right? The finite scale. Then there's a associated energy, okay? Because of the two plane insertions, so you have to deal with these modes. You carefully subtract some modes, then you get a non-trivial cosmic energy. But the point is that cosmic energy is also divergent. Okay, just do the calculation carefully. The cosmic energy is also divergent. Okay, but we don't quite worry about that. Okay, the cosmic energy is already that experiment is already performed. Okay, we can do experiment to observe the so-called cosmic force. Okay. So you see, the point is we measure the cosmic force, not cosmic energy. That's the point. Okay. So what is the cosmic force? You learned in your high school, right? What is force? Let's count the unit of the force. Force means you move, you use this force, to move along a distance, you get a work, right? The work has the same unit of energy, right? So that means what? That means force is defined by take a derivative of the energy with respect to distance. Okay, that's the force, right? Then you see, even the energy itself is divergent, but when you take the derivative with respect to the distance, okay, suppose this distance is a, okay, then the divergent piece is gone, okay, because divergent piece is constant, okay, then it's gone. Then you get something finite. Then just compare the customer force with the experimental. Then you find the perfect agreement. That's it. So you think the real world is trying to teach us, okay? We should really only care about the observable, okay? Rather than search for the mathematical completeness, okay? Well, maybe some other day, if you develop a more powerful trick, maybe even go beyond quantum field theory, okay? Suppose you are next genius. You develop some theory, then you don't need to use this renormalization program. Then congratulations, yeah, maybe it's possible, okay? Then you have both mathematical completeness and also physical prediction power. Then it's very good. But our current knowledge is we didn't really succeed in that, okay? But we know more important thing is the physical prediction. Okay, trying to compare with the experiment. That's the whole point that we're doing physics. Okay. So in that sense, we have to carefully distinguish what is observable, what is the form of mathematical divergence. That's not different. They are not the same thing. Okay, they're different. Okay. So this is what the customer energy taught us. Okay, customer energy. This is really a good example. Wherever you have confusion, you have to go to this example. Okay. This example, this customer force example, is calculable and it's already verified by experimentals. So it's true. We have to learn from it. So based on this understanding or intuition, the program, so we developed something called the renormalization. It's a program. Okay. The program of renormalization is to hide the infinity and to predict finite observables as function for other observables. Okay. Yeah, this is the more careful, more detailed description of what is the renormalization. Okay, renormalization is a program. It's a program, or the program is to get around this infinity. Okay, we will see examples, many examples actually. It's not just words. Okay, you will see indeed there's a mathematical program. You can achieve that. Okay. And as said, we were more interested in the prediction. Okay, so we predict finite observable functions of other observables. Okay. Okay. So what does this really mean? This means suppose you are a theorist. Now you have a friend who is working on experimental lab. Okay, they don't know much about the theory. Okay? So then how do you know your theory is successful? So you should try to connect it with the experiment, right? Then how you even talk with your experimental friend? Okay. Okay. For example, now if you are talking about okay, I have a parameter in my Lagrange. Your experimental friend don't understand what you're talking about. For them, I mean, everything, if they can measure something, they will believe it. Otherwise, they don't trust. Okay. You should really, even yeah, you should really, even you talk about some parameter, you should ask your experimental friend. Okay. Try to measure it, right? At some point, then you do some experiment. Okay. Do some experiment. And measure the coupling, for example. Okay. Coupling is one typical parameter in this game. Okay. Okay. Then what you really should do is ask your friend and say, okay, please measure this coupling. Okay. Okay, he measures something, do one experiment, it tells you, okay, this is my number. Okay, I get something, some 0 point blah, 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 as a number. Okay, so this is a reference coupling. Then you should, based on this kind of measurement result, then use your theory to predict some other. Okay. Then if you could do that, then your theory is successful. Okay. Okay, not something else. We're not the God. Don't, trust too much to say, okay, I have a theory to explain everything. Okay, I don't need to do any big, just one theory and once for all, and predict all the parameters. Well, that's not possible. Okay, theory has to be tightly connected to the experiment. Okay. So the theory is like some box. You have input and output, right? That's the point. But even your input, you should ask your experimental friend. Okay, measure it and take this as input. Okay, then put it into the box. There is output. Okay, from the input to output, that's your power of your theory. Okay. You shouldn't just imagine that I have a single theory. I don't have any input. Then I can tell you whatever experimental result. That's not possible. You should have input. You should have input. The input can come from many different places. It can come from the current knowledge, right? For example, it can come from the some result tested many times. Okay, okay. For example, the photon is massless. This could be taken as input. Okay, we believe this is correct, right? Because it's consistent with many experiments. Okay, so we know this is correct. Then you can take this as input. Okay, okay. You can also the input can also be with some amplitude, like experimental, right? Some amplitude. If you do just a collider experiment, okay? So you measure the amplitude. This kind of some amplitude you can also take as input. Then you get output. Okay. So what theory does is that from the input, give the prediction of this output. Okay. This is the power of the theory. Okay. So this is just a word, right? Because conceptually this is a little subtle. So I spent say a few minutes to explain it using just the words to explain this idea. But of course, we should look at examples. We should look at examples. Okay. What is the example? So let's just start from simple example. Yeah, for theory. We'll say the lambda by 4 theory. Okay, lambda by 4 theory. So for this theory, we already learned how to calculate this amplitude, right? The primary rules. For example, at tree level. At tree level, if I want to calculate this amplitude, okay? This is the pi 4 theory. This is the pi 4 theory. There's 4 interacting vortex, right? At the tree level, this is the simplest 2-2 diagram, okay? This is the simplest 2-2 diagram. So we know how to calculate this amplitude. How to calculate this? This is 2-2 scatter, right? So for this diagram, what is the IM? This diagram.
Lambda
Yeah, just minus I lambda, okay? Right? Following our Feynman rules, okay? Now we are asking the amplitude. So for this diagram, this is the answer, okay? So answer. Now, as said, we want to discuss in detail the divergence, okay? The divergence cannot come from tree level, okay? Divergence must come from the loop level. You have you have to go further to calculate that. So at one loop, F channel, for example, then we have the diagram like this, okay? See? This is the 5-4 one loop diagram, right? And this is the S channel, so this is from left to right, okay? And there's a P1, P2 coming in, okay? P1, P2 coming in. And together form a one loop, and then the outcome P3, P4, okay? So what is the amplitude for this one loop? Let's look at this IM2, the IM2. So follow the Feynman rules, right? Right on. For each vertex, we should have minus I lambda, right? So we have 2x squared, no? X squared. And there is a loop, okay? There's a loop, okay? So you should have an integral. So inside the integral, you have two internal line, right? Internal line means you should include the property. Okay? So there is a property term, right, over a squared plus I epsilon. There's also a property term, I over p minus k squared plus I epsilon. Okay? There are two propagators, right? The p is the total momentum, p1 plus p2. Okay? So this is the two propagator. Then you have to integrate over this free momentum k, right? Free momentum k. Is that correct? Okay. So this is k. Okay. This is p1 and p2. p1 plus p2 is p. So there is a p minus k. Okay. P minus squared. Now you have to take an integral dk to the force. Okay, is this enough? Or to do more? There is what? There's a symmetry factor. What is the symmetry factor? 2. That's right. So you have to divide 2. Okay. By 2. This is the result. The result. The result. Now, in principle, and just after a few minutes, we will calculate this interval in great detail. But for the moment, we want to use this example to illustrate the renormalization idea. Let's go very quickly to try to guess the result. Okay? So what should be the result? Let's try to guess what should be the result. I mean, the result, also this integral, what should be the result? First, the result should be Lorentz invariant, no? Because this is the amplitude, okay? It's observable, okay? It's observable. So this should be Lorentz invariant. And the k is integrated over, then the result should be a function of p, no? P is your input, right? Actually, look at this integral, p is the only input, okay? Okay? So the final result should be Lorentz invariant, just means the final result should be the function of p squared. P is 4 vector, okay? It's not depend on the 4 vector, it should be depend on 4 p squared, which is Lorentz invariant. Now, this is the S channel. Actually, S is nothing but p squared, which is p1 plus p2 squared. Okay? So the final result should depend on S or P squared. Okay. For Lorentz invariance requirement. So what more? So let's look at the integral. If k is very large, okay? If k is very large, then the PV can be ignored, okay? Right? So what? So how do you estimate this integral? When k is very large. When k is very large, do you know how to do this integral? When k is very large. Oh, we can do it, right? When k is very large, then this integral becomes a dk to the fourth over a k to the fourth, no? Right? That's the integral. Then after 1 second calculation, you realize that this is a divergence when k is close to infinity. Okay? This is divergence. So which kind of divergence? Do you know which kind of divergence? Because you have dk over k. You have dk over k. dk over k is which kind of divergence? Come on, this is your first year integral course. Okay. So when you have dx over x, you have which kind of divergence? Log cos. Okay. Okay, because you have the integral 1 over x, so you get the log x. Okay. So it diverges. As log k. For large k diverges as log k. Okay. And combined with these two, and also after small calculations, one can try to arrive at the final result. Okay. For example, one can show. Yeah, we will calculate this one later. One can show. The trick to calculate this integral, I can first take the derivative with respect to s, okay, of this im2, okay. So one can show this d partial s m2 s, okay. So we know m2 must be a function of s. Okay. We know this derivative is equal to minus lambda squared over 32 pi squared. Okay. Well, of course, at this moment, we just accept it. Yeah, I'm going to, just a few minutes later, I will just try to derive this one, do this calculation. But at this moment, you just accept it. You can easily show this is correct. And this is also justified with the logarithmic divergence, right? See? Right? Because partial s is 1 over s. Okay. The integral you have log. Okay. So what? So if you accept this derivative result, which we didn't derive, we will derive. Okay. Then you just perform an integral. Okay. With this result, if I tell you this is correct, then you can immediately write down m2s. What is m2s? Minus lambda squared over 32 pi squared log s. And not only this, plus what? Integration constant, right?
Yes.
Integration constant. Okay. S is some input. Of course, S is not divergent. But we also know this M2 must carry divergence, which is logarithmic divergence. Okay? Okay? Then I can immediately write the full result must be M2 equals to minus a lambda square over 32 s squared log s over lambda square. Okay. Okay. And this lambda represents this divergence. Okay. This lambda is something called UV cutoff. UV cutoff doesn't mean UV cutoff means very, very high momentum cutoff. Okay. In momentum space. Okay. So this is what is the meaning of the lambda. You see? Now you ask me, how do you know? This is just some constant. There is a numerical coefficient. How do you know? It's just precisely coming into this log in this form. Well, if it's not, then I can redefine lambda. Okay, lambda is just some UV cutoff. You can shift it, multiply with factors, whatever you do. But indeed, we know there is a logarithmic divergence. Okay, the logarithmic divergence shows as lambda goes to infinity. Lambda goes to infinity is fly. The divergence. Okay. You see, it's just if you know how to do integral, then this is immediately natural for you. Just whenever you do integral, if the integral is divergent, you can make a cutoff somewhere. Okay. Okay. The cutoff by definition, the cutoff replaces infinite. Okay. Okay. For example, you integrate some x from 0 to infinity. Either near 0 or near infinity, you have some divergence. Okay. But in order to avoid those divergences, you just put the cutoff. The cutoff means you don't really go to 0 or infinity. Okay. You get epsilon close to 0. Okay. Or you get 1 over epsilon close to the infinity. Okay. That kind of epsilon is essentially the cutoff. The same cutoff here. The cutoff here is just in momentum space. So you can treat it. This is a very, very, very high energy momentum, P. Okay. That's it. Some P, okay? This P compared with the ordinary momentum is very, very high. This is the meaning of lambda. So you see, we guessed this result. Of course, I jumped somewhere. We will justify it very soon. So let's accept this result is correct. Okay. And at that, mathematically, you can push this lambda goes to infinity. Okay, essentially lambdas come from the integration domain. Okay, you have to do some integrals close to the infinity or touch from 0 to infinity. Okay, but in order to make this integral to the finite, I don't go to really go to infinity, but I put a couple. Okay, a couple. But you can always think, you try to push this cutoff to go to infinity, then you see this divergence, okay? From this log 1 over lambda squared, okay? This is a so-called logarithmic divergence. Right? Now, let's start the program. So what is the program? Well, start the program. Which program? That program. Okay. Now, from this example, we want to go through the program of the renormalization. So what do we do? As I said, we want a program to predict an observer out of other observables. Okay. Okay. So for this example, as you can see, the very important question is to ask what is the meaning of the coupling? Okay, for the coupling, for the coupling. We want to understand better the coupling. Okay? As you can already say, that's why we want to look into this diagram, because this diagram is proportional to the coupling. You see, it's proportional to the coupling. Okay, and this diagram you can view that this is the experimental and this is the theory. Okay, this is your real experiment because you can do it. Okay, you can do this to scatter in the lab. Okay, but this is your theory, right? This is because lambda comes from the Lagrange, right? This is your theory parameter. Okay. So we want to try to connect these two. Now you ask your experimentalist friend, what is the coupling? Okay. Because a priori you don't know. At the theory you don't know. You don't know the lambda should take it as 0.5 or 0.1 or 0.2. You don't know. Okay. You have no idea. Okay. Okay. The only way you can try to understand or fix this lambda is to ask your experimental friend. Okay. Then you ask your experimental friend, what is lambda? Okay. This is the first question you should raise. Now your experimental friend know nothing about the experimental theory. Okay. Know nothing about the theory. Then the only thing they can do is just try to collide these two particles. Then your experimental friend realized, okay, it seems if I try to do this 2-to-2 scattering, it seems this amplitude is very close to lambda. You see, at this tree level, they are even equal. Right? At those levels, corrections. Right? As we learned from the Feynman diagram calculation, up to one loop level, what you should do is you should add up this one and that one, no? Right? Because these are two diagrams. You have to include both. Include two diagrams means you have to add up. Okay? You add up. Then what you should do, the total amplitude is the IM1 plus IM2. Okay? Then in terms of lambda, you realize that this is roughly lambda plus lambda squared. Okay? If lambda is small, then you should understand that, okay, this is some next order correction, right? If lambda is 0.01, then this is pretty much small compared with this first order, right? Okay? That's what you should understand. Now, the answer comes from your experimental friend is that your experimental friend that is they can define the answer comes from them is let's define the answer from your experimental friend is because they don't know, again, they also don't know what is the a priori value of lambda. Okay, the only thing they can do is just perform experiment. Then your experimental friend say, let's define something called renormalized coupling. It's just a name, never mind. Okay, let's denote it by the lambda r as minus n at a particular momentum is s equals to s. Okay, why? Because it's the oscillation is coming from here. Okay, you see, here's I, here's minus I, so m is related to minus lambda, right? So one way for your experimental friend to define lambda is try to use minus m. Okay, okay, because minus m they can observe from that. Okay. So your experimental friend say, okay, I can give you some value which you may call it lambda r as minus m as some particular s. Okay, that's the answer from your friend. Okay, so let's do it. This means as a definition, lambda r equals to minus m as 0. Okay. Now, of course, minus m as 0, we can just compute it, right? We compute it as that. These two amplitudes should add up together, and this equals to lambda plus lambda squared over 32 s squared log s0 over lambda squared. Now m means m1 plus m2. Okay, m means m1 plus m2. You get this one. See, Get this. Get this. Yeah, of course you get some higher order, but I just stop with the quadratic order. This is what you can do. Okay. Now, from this equation, one can solve. From this equation, one can solve lambda in terms of lambda r. No. Okay. And it's this equation. I can reverse solve this lambda in terms of lambda r. No. And since this is the perturbation, you immediately get lambda equals to lambda r. Okay, let's do it very slowly. Let's say, suppose this is supposed to be the correct result plus some higher orders. Let's plug it in. We don't know what is A, but let's just plug this in. Okay. Plug this ansatz to here. Then make left equal to right. Okay. Then you realize that you can solve it. Plug it into. Plug it into this star. Everybody can solve that one, right? It's a kindergarten mathematical problem. You can solve it, right? You can solve it. So what you get is, let's say, let's go, let's try this kindergarten problem. Then what I will get is something like this. Let's sort it out. Plus lambda r plus a lambda r squared squared over 33 y squared log 0 over the okay. Okay. The point is now I only keep the order to square root and throw away some higher orders, and this will be fine. Okay, see? Now, up to quadratic order, left has to be equal to right, then this A has to be minus this guy, okay? See? So A has to be minus this guy. Now, eventually we know we solve the lambda equals to lambda r minus 1 over 32 I squared lambda r squared log 0 over lambda squared. Okay. This is the answer. So we get the expression for lambda in terms of lambda r. Okay, starting from here. Here the expression is the lambda r in terms of lambda. So we solve it reversely. Okay, we solve it reversely. We get that expression. Now, so what's the point? Why I need this one? Why I need this one? You see the magic? Now, if you can express lambda in terms of some other physical variable, okay? Remember that lambda r is your experimental friend. It has a value which your experimental friend tell you, okay? Which is really the observer. Okay? So you can use this formula. You plug into the original amplitude result. No, original means what? Original means arbitrary, okay, I didn't write that. Let me put it here. Original result means if I want to measure the amplitude M at the arbitrary S, okay? At the arbitrary S, it's not S0, it's arbitrary S, okay? This is from the original result. This is what? This is M1 plus M2, no? Right? So this is M1 plus M2, which is minus lambda, minus, which is minus lambda, minus that one, okay? Minus lambda squared over 32 r squared. Log S over lambda squared. Right? This is your original amplitude at arbitrary S in terms of lambda, right? Now you have an expression, you have a result for lambda. Just plug in this into this lambda, okay? Plug in this lambda into this result. Then you get your prediction. You get power to give the prediction, okay? You see, this is the game. Why? Now you plug in this lambda. You can express the amplitude at an arbitrary energy scale only in terms of physical observers. Okay. See? So what do you get? So eventually that just try this game. Okay. This is not problem. Okay. So eventually what you get is square 0 over square minus with some higher, we don't care. Okay. Now you see magic happening. This capital lambda is gone. Okay? These two cancel. So this result does not depend on the cutoff. So this result now becomes minus lambda r minus lambda r square 32 pi square log S over S0. Okay? No cutoff. No color. This is the result. Now we use this result. It's really the prediction. Okay, this is the prediction out of theory. This is the prediction. Why? Because this formula tells you if you do experimental at S0, okay, you measure once your amplitude. Okay, you take it as your lambda r, then from this formula, you can know whatever amplitude in other scales. Okay, this is the prediction. The prediction. It's very simple. It's not. Yeah. I think the point is to try to understand the program. Okay, what do we really do here? Because of this, we see this is the predict. This is the predict one observation from another. Okay. From another. Now, if you want to go into more details, there are more interesting observations you can see. Okay, you can see, for example, here. Okay, you see, if you agree lambda r is finite, because it's a field observer, right? You observe it, your experimental friend tells you the values, definitely finite. Okay. Then you see that this expression suggests because this is finite, this is finite, and this is divergent. Okay. If this cutoff is close to infinite, then this is divergent. So it seems the original lambda includes a divergent. You see? You see? Right? This is the original lambda. Sometimes we call this is Bayer couple. bare means it appears in the first Lagrangian, okay? That means bare. When you first write down your theory in the Lagrangian, the parameters called bare parameter without doing any further much, okay? These are the bare. So look, so it seems the bare coupling observer some infinity, okay? Right? So this is one reason we call this renormalization, or hide this infinity. We hide this infinity into this bare coupling. But eventually, if you express everything in terms of the renormalized coupling or physical coupling, okay, then there's no divergence. Okay, this is the trick. Divergence disappeared. You don't need to worry. Okay. Don't need to worry about that. Okay. Do you have any question about this little program?
So when we do a measure and we get the lambda r,
yes,
or not lambda.
Lambda r, yes.
So
this is my definition.
So the lambda is where we cannot know.
Lambda is
so the pure lambda, the first lambda, and we cannot know it. Because when we change the lambda r to lambda, we still have a big lambda, yes.
Where? Yeah,
如果我们把它换到那个，就是把lambda r换到lambda的时候，它始终还有一个，就是它是存在一个阶段在上面。
Right. You mean this one, of course.
所以用这个方法的话，就是。
The point is lambda itself contained a divergence. It cancelled. So eventually this is finite.
对，就是初始的lambda我们是无法知道的。
Right. So that's what we call bare coupling. Okay. If you disregard the experimental, if you don't know anything about experimental, you have no idea. I mean, you don't know any. You don't know real physics meaning of your bare coupling. So in that sense, bare coupling is not that physical. Okay. So it's not closely related to your experiment. It's just something appeared in your formal theory. Okay. It's just something appeared in your formal theory. OK，
老师，但就这个地方，闪射振幅也不是一个官方用的，就是它。
Strictly speaking, yeah, but amplitude is among all these quantities is the closest quantity to observe. The real observer is cross section. Yes, all right. But amplitude is almost. But strictly speaking, amplitude itself is not a direct physical observer. You're right. Physical observer is the cross section, but they are closely related.
所以实际上你怎么确定说 ms0 我是能够知道的呢？如果说你要重新定义这个东西 ms0 上，说明你那个 ms0 应该是在实验上可以确定的，对吧
？Yeah. From cross section, we can derive this amplitude. Yes.
Okay.
From cross section. Any other question?
In the expression of the final ms, can lambda be safely cancelled in higher order terms with respect to lambda r?
Very good question. Yeah, you should check it to higher orders. Yeah.
Yes.
The answer is no. The answer is yes.
Okay.
The answer is yes. Yeah, the answer is yes. Any other question? Yeah, you should go to higher. That's a very good question. You should go higher orders to play this game. Then eventually you will get this dot. Okay, you get this dot. The dot depends on you calculate more loops. Okay.
It is always guaranteed in an arbitrary diagram or
arbitrary what?
An arbitrary Feynman diagram or an arbitrary theory.
Perceptually, I think.
Okay.
Perceptually, I think. You can push this game. Okay. So this is the idea But of course, the renormalization theory or renormalization program is very, very deep and sometimes it's not easy to understand everything. So you should try to, after this course, yeah, you should, if you are interested, you should go into this many different discussions about the renormalization program to understand more deeply. Okay, this is just the first exercise to tell you how this game works. Okay, how this game works. So let's give a few remarks. This is important chapter. Remarks. The UV color, which is that the capital line, is to regulate the divergence, right? Okay, this is very obvious, right? It's obvious. So, by divergence, you can meet many different types of divergence, right? Right. This is only a log. This example is only about a log divergence. Sometimes you can, yeah, sometimes you can have some divergence, for example, the lambda square. Okay, this is also a divergence, of course, if lambda is infinite. Okay, you can even have some higher powers. Many different. Now, whatever. So the clean thing here is that if you put a cutoff, then you can explicitly see which type of divergence you have, right? That's the power of the cutoff. So in that sense, the cutoff is helpful to regulate this divergence, okay? Just by seeing divergence doesn't mean much, okay? Divergence can be classified in different ways. Some divergence is lower, some divergence is higher. Just but in order to really specify this divergence, regulate this divergence, it's better to put the cutoff. That's the useful cutoff. And as you see, the cutoff dependence dropped. Yeah, this is related to the question just asked. Okay, the cutoff dependence always drop out of physics predictions. Okay. And the parameters in the Lagrangian such as couplings are not observers. They are not observers. They also dropped out of physical predictions. The coupling constant. Also dropped out. Okay. Dropped out of physical predictions. Yeah, these are the three remarks. So in the remaining time, we'll go through some other examples. Okay. Eventually, the example in the real world, and see how this program works. Okay. And we also want to seriously take this input. Okay. To try to develop some trick, some calculation tool, how to deal with this loop integral. Okay. because as mentioned last time, there's a huge community just to try to compute the loop diagrams, okay, or this amplitude. Okay. So there are some tricks you have to know in order to seriously calculate that integral. There, we didn't really do that. We just guessed the result, okay? But we want to do that seriously. For the next example, we want to solve another theory and another diagram. Next example, it's bicubic theory. Okay. We discussed one example by 4. The bicubic theory, we know the Lagrangian is given by okay, this is my Lagrangian. This is my Lagrangian. So since this is a bicubic theory, if you want to talk about the simplest one loop diagram, so I have something like this. You see? Now I don't have by 4. Okay, by 4 is means like this. Vertex is 4 lines. You see? Now I only have 5 cubic. You can only have 3 lines in the vertex. The simplest one loop is this diagram. Okay. Okay. Well, let's say I want to calculate this diagram. So this is pk, and this is k and minus p, or p minus k. And this is p. Now, usually use your knowledge, Feynman rules, to calculate this IM in this case. Okay. So what is the IM in this case? It has to be function of p, right? The p is the input. What is this? Again, like before, let's do it. So it has to be an IG, okay? There should be an IG for each interacting vertex. So you have 2. I will take square, okay? So IG squared. Now there's a loop. You should have an integral. And inside this loop, there are 2 propagators, okay? We should write down here. So one is, let's say, let me note as a minus p squared minus m squared plus my epsilon I. And another propagator is p squared minus m squared plus my epsilon. Okay? Or maybe p minus k, doesn't matter. It doesn't really matter. Okay. Because you take a square. Okay. Now, you have integral over k. Right? And eventually you have a symmetry factor. Very similar to the previous example. You see, even you look at the integrals, okay? Now, the little more is we include the mass here, okay? Very similar to the integral. Even though these 2 series is different. But if you look at this in one loop integral, the integral is really the same. Now, how to calculate this integral seriously? Okay, don't you just guess. Calculate this seriously. Now there's a trick to calculate this one. This trick is so-called the Feynman parameter trick. The trick says that whenever you have 1 over AB, there's the integral expression for this one. 1 over AB is equals to the integral from 0 to 1 dx, 1 over A plus B minus A times x squared. Okay? This trick. Use this trick. Just some trick to do integral, okay? Now, the next 30 minutes, we forgot about physics, basically. We want to just discuss how to do the integral. There are a few tricks. Forget about physics, just do how to do the integral. We use this trick. We use this trick, meaning what? We should try to connect this A, identify this A to the, we try to identify this A to this part, okay? Right? We should try to identify A as this part, and B with this part. Okay. This 1 over AB equals to this one. Okay. So you treat this is A, this is B. Then the integrand can be turned to another this form. Okay. Another this form. And what I should try to do is switch the order of this integration. Okay. First do this integration. Always. Okay. And then you can realize that you can easily calculate this. So let's do it. Now there are some subtle conditions to that this equation is true. Okay. In some very special situations, this is not quite true, but you can rule out those possibilities. It doesn't matter. Basically, this is true. This is true for any complex number AB, as long as 0 is not contained in the segment. Okay. Okay. The AB is two number. Okay. Okay. This is the identity. This is the identity. This formula is the identity. But for this identity to be correct, to be true, AB are 2 points, right? AB are two numbers in the complex plane. AB are 2 points. In order to guarantee this is true, you should make sure 0 is not contained in the line segment connecting AB. Meaning that if you connect the AB, okay, you make a line segment, 0 cannot be on the segment, okay? It's the only condition. So you make this identification, then you just go straight forward. Actually, it's hard. Then A plus B minus A times X will be equal to P minus K squared minus M squared plus I epsilon plus K squared minus P minus K squared X. Okay? Let me do it for you. Just a straightforward exercise. And this equals to okay. I want to complete the square, okay? Then what I get is this. I want to complete the square. Okay? Now you realize that your IM loop function of P is the G squared over K integral from 1 to 0 dx 1 over this k minus p. Okay. So this is the result after I use my identity or find my integral trick, right? So identify this is A, this is B. This is the result. Right? This is the result because the right hand side the denominator is a square. So it's a square. Okay. So this is nothing but the A plus B minus A times the x squared. Okay. So it's a weird trick, right? I mean, it's kind of something that looks more complicated. Okay. So why we need it? Why we like this trick? We like this trick because now you see. Look at it carefully. This integral. If I first do this k integral, nothing else depends on k, right? Only here there's a shift for k, right? Okay. So k is shift does not change the measure. Right? Okay. So we can shift it. We can shift the k to k plus p times 1 minus x. Okay. Okay. We can do this trick. But not change the integral, right? Then this IM becomes d squared over 2 integral k from 0 to 1 dx 1 over d squared minus m squared minus p squared x bracket plus m. Okay. So this will be the integral after shift. Now it comes to the point. We do know how to do this kind of k integrals. Okay, we do know. Okay, because all this, even though this is complicated, it's nothing to do with k, right? You can treat this as some single object. Okay? So this kind of integral is basically say that this is the dk to the fourth integral. Let's first forget about this one because I want to pull this out. First do k integral, okay? So for this k integral, the object we want to integrate is 1 over k squared minus some object plus I epsilon and then square. Okay? So this is the integral I have to do. If you know how to do this integral, then congratulations. Done. Okay. Right? Is that clear? Is that clear? You see, the magic here, we go this several steps. It's just to try to turn these two pieces into a single, right? A single object, but with some power. You see, right? If you don't do this trick, then you have two pieces. You have two. The two pieces are different. Okay. Now, if you use this trick, eventually you come to this integral. Okay. So let's talk about how to do this integral. Okay. There's a very nice story to tell you, to learn how to perform this integral. So how to do it? Do you know how to do this integral? Can you try it? So this integral is nothing but, let's pick this out. The problem now becomes how to do some integral looks like this. Okay, some look like this. Don't worry, this delta. This delta is not the operator. Delta is just means that part. Delta means just some this part. But this part has nothing to do with k. So you can view this as a constant. Okay. This is some constant. Some constant. This is some constant. Now this is the problem. You know how to do this integral? I want to do this integral precisely. I don't want to just say take k goes to very large, like before you estimate it. I want to do this very precisely. So how to do it? Before you do it, before you calculate it, you should first understand it, right? To understand it, just to remind you, many weeks ago, we learned this kind of integral, in particular this I epsilon, right? Remember that? This I epsilon is here, essentially because this dk to the fourth carries like a dk zero, no? Right? Right? It carries a dk zero, right? And the dk zero, if you don't turn on this I epsilon, the dk zero has a potential poles. Just dk zero, you want to do the integral along the real axis, right? Then there's potential two poles. We don't know, if you don't specify this contour, then we don't know how to give a unique result, right? Because there are two poles. It's like unified. That's why we introduce this I epsilon, right? So the I epsilon somehow shifts these poles, right? It shifts properly in a proper way, shift these poles. Then there's no difficulty. You can go along this real axis, okay? It's equivalent to say you choose some contours surrounding these poles. Okay, this is what I epsilon does. This also means that this four-dimensional integral is not in a Euclidean space. Okay, it's not in a Euclidean momentum space. Okay, because K1, K2, K3 is different from K0 in the signature. Okay, is that clear? Right? Essentially because of that, right? Right? If it's in a pure Euclidean momentum space, you don't have some contour or whatever things, right? You see? Right? So you cannot just simply view the, okay, this is just the four-dimensional integral. Let's treat this k like some x, then you do the four-dimensional Euclidean space integral. That's not correct. That's not correct. So this is the point. So we have to really discuss how to turn this to some ordinary integral. So this means that there is a pole. So let's first, again, here we have to deal with the power is 2. Let's relax this 2 to n, okay? If I know in general this integral, then of course I will know, okay? I may know this 2, n equals 2, n equals 2. Let's first deal with this one, okay? So for this one, the pole is the pole, okay? This part does not change the position of the pole. So the point is the pole exists for this integral, okay? This integral. So you can work out the poles. Where are the poles? The pole is here. The pole is the k space vector square plus delta minus I epsilon. Okay. You can check it. This is the pole position. Okay. This is the pole position. There's a pole. Now, because of this, you can figure out the contour or the poles in the complex plane. Okay. Now, where are these positions? This is a real number, okay? Okay? And this is the positive, a real number. This is minus I epsilon. So where are the poles? So the poles should be somewhere here. Somewhere here. You see? This is the plus minus real part. Okay? And for the first, this is the minus I epsilon here. Okay? And for the minus becomes plus. You have a plus I epsilon here. Okay? So these are the two poles. So for these two poles, you do your integral, meaning now you can safely go in this way. Yeah? This is your control. This is your control. Okay? So you go in this direction. Okay? This is so far the definition for that. This is only to help you to understand the meaning of this integral. Okay? This is the meaning of this integral. Okay? There are two poles, and this is the control. Okay? with I epsilon, this control get avoid these two poles. Okay, so it's well defined. Now there is some trick. The trick is I observed you can close the contour in this way. Okay, then close the contour in this way, right? You can easily justify this arc, this two pixel arc does not contribute, right? From your learning your complex analysis, okay? And then this contour integral equals to this contour integral, okay? Up to sine, okay? Okay? Because this is the only two poles. There's no pole in this two region. So the entire contour integral becomes 0. And these two pieces of arc are trivial. So now we can turn this line, this integration along this line equals to minus the integration along this line with this direction. Okay? So I close the contour in this way. Okay? Is that clear? So I turned, in that sense, I turned this integral to another integral along this one, along this line. This is the imaginary axis. Okay? This is the real axis. You see? So this is the key observation. So the integral over the real axis plus the integral over the imaginary axis equals to 0. Okay, equals to 0. Therefore, we can weak rotate k0 to I k0. Okay, we can do this. We can do this replacement or rotation. Okay, I can change k0, set k0, turn this k0 to I k0. Why I want to do this? Of course, eventually you're not saying right. The reason why I want to do this is because after you do this, then you really become a pure four-dimensional Euclidean integral. Okay? Right? With the Euclidean signature. You see? Right? Okay, previously the Lorentz signature. Now you do this rotation. Okay? Okay? You do this rotation, then K0 becomes like a P1, a K1, K2, K3. So in this case, K squared now becomes minus K0 squared minus K squared. We can denote this as minus Ke in order to distinguish the previous K. Now this is the Euclidean K, four-dimensional Euclidean K. Okay. So another advantage, if I do this rotation, the integral now becomes along the imaginary axes. Okay. Because now, if you do the integral along this imaginary axis, then it's nothing to do with this I epsilon. Okay. You can set epsilon equals to 0. You see? You can set epsilon equals to 0. It's okay. Because now epsilon, you can safely set epsilon equals to 0 because even at epsilon equals to 0, these 2 points does not touch your contour anymore. Okay. Okay. So that's another advantage. You set epsilon equals to 0. You can set epsilon equals to 0. Now the thing becomes simple. Now that four-dimensional momentum integral really becomes a simple integral. Yeah. Let me write this and then we'll have a break. The previous four-dimensional K integral, for example, if I want to focus on this power is 3, okay? You can do it. After this rotation is I dt. Okay. So it becomes this, and this integral is doable. Okay. This integral is doable. You put it into mathematics. This integral is doable. And you get the result. This integral is 32 pi squared. Okay. This integral is doable. Okay, this is the ordinary Euclidean integral. Okay. This is the ordinary Euclidean integral. It's doable. Now, with this in mind, the previous question is obvious, right? Why? The previous question, where is the previous question? The previous question is how to do this, how to do this, how to do when n equals to 2. Oh, this is the original question, okay? Now you're saying there's no direct answer, but it's an indirect answer. We know this is 3, okay? But the point is the 2 is related with this 3, okay? How they're related? There is a relation. For example, if you denote that this is the I delta defined in terms of power 2, then you have the d delta I delta will be equal to, you can check yourself, will be equal to dk 4. 2 over a squared minus the plus epsilon. So 3, okay? Power 3, right? And you know this, so it just means you know the original integral with the derivative with respect to delta, and it equals to minus I, according to this result, 16 I squared over delta. Okay? So you know the derivative. You know the derivative, and we justified the previous conjecture answer. So derivative is indeed this. Then you know the original result by combining with the couple. So this is the answer. Okay. This is the answer. So you plug into this one. Okay. Right? You plug in this one because delta is nothing but this blue line. Okay. You get the answer for this k integral. Then eventually you do the further integral over x. You get the final result. This is the idea. Okay, let's have a break. Then we will continue. Yeah, let's have a break. We'll continue in 2 minutes.
他用了一个积分的规模，然后呢，小妙计，从然后我走了人，所以你为什么不能其他的太它挺贵的，我当时组正好贵结算，讲不开给那个那是解决普通话节节最紧张，而且是比那些是能这么事，那个比后面两个怎么统一呢？讲不了，所以说是不是可以放在本来它的穷列成，把这个东西，把这个东西关于 S 的这朗达2，这个我觉得正好这种在关于一个 G 的多这个或者为右的这样讲，就这儿不再去分析，又不是动用了，都你把 给 R 给 S 用的一个场，
这个对吧？完全这个基本确实什么也在说什么
我现在
没有了，跟你给放
在，
这方面就这样。
我只是在 verify 这两个没有。
你在说啥？我这个
刚才是0吧？那个是1，这两张单
啊。
但是
啊，我也是，因为 TCU 的做起来很小啊。对。
不是你直接记这个会有什么问题吗？
直接这个会变成，我给好像会变成这个东西。那个我
这就是商品，这个非常开心，没有
真人售出，
所以说就是这个，这个就是你的，所以说你上一代是这个，就你上一代这个，其实我感觉就是你按照时间算一个那种自己不会写，就做一个测度的话就行了，就是特别在一起。哎，自己这个可能没有一个放大的。
看我那个，
主要就是想把这样子的避开，这样
的它这个数就 K 了嘛，
又可以绕开所有步。
啊，而且数的话就是一个纯的5切一点的，
是啊，散掉他们就不能说体验，
按那个直接3维球面，面角，在 K30。不然的话，我们敏智空间很显得是这样子球形化。换
马上就进来一个欧式
啊，对，太欧式了呀。所以它
它那个度规变成负一了。
对。
然后换一个。是要是不是那这种对它换语言就对，如果我所有图要你要就把这张图算对，那张图算起来的话，每一张图都比类似那种
看到来不来？
对，同一个同一个，是这个啊，还是消掉的。
这每一阶的来不来前面的系统
都会消掉的，是一个会消掉的。
正常的话就是每一阶
一起来都后面不去，整体位置无限，对。平台上受环还去过等一下，不去。你逆取不思还右取。
啊，什么时候变成山？
就一个。哎，那这个不仅那个群啊，您这个群，还有另外有一个经历，就是更多更一些新山，我是毫无发现，或者是拉，如果你算3个免费几万钱嘛，就比较好。KFC 免费 KFC，今天晚上什么？给我买这个款的买上去，我从新的所以我就
就我今天上2，我就
跟我说关系点什么？
好算吗？好算啊，好算就可以算。算吧。就是说，我们正常一般人把这种东西交给 AI 的，
就你不用管那个
一般人写或者用这个手段，
就评分里面那个东西可以去把
杯子这种杯子，
我看一下，
我跟你说，结果是这个。
并不能理解。
结果这个，
然后是上面是 K 的，现在 U 加的，
你现在有没有转动啊？对，它会有个高阶项，像
我把前面就全扔了。
或者更好，你有你那个是一点 app 并不像来看这个，
那我在按平方来算，
插一个系统，
我直接从这开始，
那无所谓。
你觉得后面你自己都可以。
你在哪儿算出这个结果？那它分母变成正数，生物穷后面。
那你的 A P 中，你的 A P 中就直接就直接扔了呀，他这边不也直接扔吗？
他是你转了以后不转不能扔。
不是你这边那个是它只是一个次数的问题，它只是个次数不一样。
我知道，我现在 现在是走的是这个价格，这个我们是不记得多，你不能这么拆，一千块那确实就
哦，对对对，
是加上那个。
那我直接算 K1，算 K1应该是没有问题。
三 K 一，
这个实验上画的是
你们这么画了个大牌，
就我就说这个就大对前面那个写还算一下，对往上，
那它会被取
你就在下面这个打码，
到时候下面这个，那你现在去找你要
下面这个不一定是会画的，
然后呢，你下午就能看到在各大
但是上面那个
这个照片，说不定在后面
下面那个原因是在玩热气
没拍完，我们
上面是平方线，下面是什么？它是对 n 次方讨论的。那你这个是可以这意思。
肯定算按
但是这样子一般这个不是下，然后
你保持的上高，
但是你这样的积分是不是应该要写？或者是按这样比如说你一般的东西表示一个，那你来自一个乘法，是它这个类似啊，它这个可以加这个一个步骤，现在还不知道喽，你看分第二个逻辑，第三个方式，然后这些你再定位到这个过程，用麻痹的原理就可以形成。我要再反过来把朗达找你学看，
那为什么是说
这个让先积分在那个
就是
压判别出 MS，
这这一大档，这个
但是我系数变了，系数以后把这个的系数压的，所以这个加上线性
哦，所以这个叫美区，跟我
它是那个
哦，系数上啊，所以就没有基地。
哦，第二个红我，他当时做的
对，这个是的，对。
啊，对，啊，不是你差个100
啊。I 等于就是说
你后面把那个等下来
一个比一不是，
然后负1等于 1等于 I 等于负 I，三次方。然后它出来是个瑞。
哦。
然后就是说，在
对，这个没有这个对对，记这个没有。
对啊，记这个就没问题了，直接。
这当时还要弄个3次方，然后再把那个导。
因为2次方还是打出来，2次方打过来加，名字不一看就是有个
一个对称对吧
？DK 除配嘛。
那我的问题是，但是这两件事类项是不掉，如果不考虑线，我怎样会有
对啊，
这边它出来个 line，然后你就是领到这个，
对啊，这就打过去。
那应该是不同的正为什么？
因为你放到球面半径左右，
这是个 S 那张图。
那这个不是关于可以加那个线钢了？
你可以啊 ，right，对啊，
对，然后你把线钢的它就
敏感一点，
单独的
一样的，
敏感一点，
这边它这相当于是，
因为这个情况下，
这里也是那出来钢嘛？
我敏感是这个它是敏感，打那个答案就是说你不让，
但你会有 S
要多这一个，就是你最后反正是来直
还是跟这个它
不会出现 U M
这个分不清楚啊，这个东西。
对。
那么你的话，一个就是把这个欧米伽 A 看作
S 换成 U，
那你就这个时候，你可以把欧米伽 A 看作它不是一个。
他们那两张图也是往都会出这种包的。
是的，是的。
就是我就是说，应该是在对称条件把这个式子，
那这个上限
线条下的话，就是它本来就是
哦，看来我们对老师基本不会。
我也是啊。
都是 A，
反正后面还有。
毕业课如果让那个是一个初中上来，他给你贴的比我高。因为他比我高。
会变量会
变成一个落变成3种。
这样也能。
这里这个配方成正比。这个是不是这都是成正比？它就这个步骤是 k 的平方，这个应该是总能给它搞上来，这个全部展开个20等于。就我感觉后面这个会不是特别显。这个
我意思是把配群的过程。这个当然可以简单了，然后简单就
这已经把那个欧米伽 A 扔掉，
这样。
不比别人上去有不行。我觉得
还是把这个，现在把这个我们要 A 这个为这个
欧米伽 A 其他方面太简单这个简单方式。
OK， 那为什么没有
对称的情况下，它可以想象这可以。这个比较大，后面又是自然而然对的。我觉得这个
我现在这条球，
因为我要去帮
X 的，
我们显示这个，就我自己觉得这样的。
Okay, let's continue. So let's finish this physical calculation. So we already computed this I delta. So what we have to do is just set delta equals to m squared minus p squared x 1 minus x. Which is this one. Then you get your IM equal to minus g squared over 32 m squared. Integral from 0 to 1 dx log m squared minus d squared x minus x over lambda squared. Okay. So we are left over with the dx integral, but this integral you can easily do it. You can easily read. So this integral can be done explicitly. For example, for m equals to 0, we can calculate this one. You get m equals to d squared over 32 pi squared. 2 minus log minus p squared over lambda squared. Okay? You get this one. You get this one. Now, so there is a funny truth. The point is, as mentioned before, the cutoff you can choose. You can choose as you like. We can shift this lambda by e to the minus 2. Okay. Then the 2 disappears. One can remove this 2 by shift in this way. Right? Then you get the now we also let's say if we want to interested in this regime p squared less than 0, okay, then one can define the q squared, another q squared equals to minus p squared. Yeah, we will see why. Because there's a first glance is there's a funny minus here, okay? So inside log there's a minus p squared. The minus appears here because don't forget the diagram we're dealing with now something like this. Okay, this is our diagram. Okay. Now if you use this kind of diagram as a T channel, then you get something like this. Okay, you get something like this, right? So you can view this as a T channel or a part of a larger diagram, for example. This way. Okay. Then in this case, the p squared is negative. So the minus p squared is positive. It perfectly makes sense if this is positive. I mean, this result can be interpreted in this T channel very naturally because minus p squared is positive. So what is this? This means there are two particles, okay? Two particle exchange something, okay? the two particles scattering, but they exchange something, okay? Okay, because this is the T channel, not the S channel. S channel, you just two guys collide, become something, okay? Collide, become something, and then decay. But in the T channel, is the two particles scattering, they exchange something, okay? If you calculate this exchange object up to one loop, this is what you have. Okay? So, in this case, we can redefine the Q squared equals to minus T squared. Then, eventually, my amplitude will become minus T squared over 32 pi squared over Q squared over 1 squared. That's it. Okay? So this is the result. And this Q square is the physical scale or experimental scale. Because this is the scattering scale, right? It's the scattering scale. And this lambda is the cutoff scale. Cutoff scale. And the coefficient is independent of the cutoff. We have already talked about a shift here, but it doesn't matter which kind of shift you're doing. The coefficient is stick to itself. Okay? This is universal. This is universal coefficient. Okay. Now let's seek for the physics of this result. Okay, let's seek for the physics of this result. As said, this result can be considered a part of a larger diagram. Okay, part of a larger diagram. Okay. For example, because now we are talking about the phi cubic theory. Okay. If we're working in QED, this kind of diagram is precisely the scattering picture or exchange particle picture for the Coulomb force. Okay, this is the Coulomb force. What is the Coulomb force? Coulomb force happens between two electrons and positive. Okay, or two electrons, they exchange photon. Okay, okay. So they're scattering by exchanging photon. Okay? This is similar, but in this phi cubic theory, there's only one scalar particle. Okay, you don't distinguish. But the physical interpretation of such kind of scattering process is these two particles, they exchange something. Okay. And now what we are computing is the one loop part of the exchanged diagram. Okay. Okay. Now, since this is the one loop part, we want to, in order to physically, in order to extract the physics or take use of this result, physics contact, we want to turn to the complete picture or the complete amplitude. Okay, because this is only a part. This is only one movie part. We want to ask the complete scattering process. Okay. Complete scattering process. Okay. The complete process is the tree level diagram. Looks like this. Okay. Right? Tree level diagram looks like this. And what is this I am in this case? I am there. The loop level. Loop level is 0 in this case. Okay. Okay. So for this, we know the result, which is the Ig squared, I over P squared. Is that right? Is that right? This is the amplitude for this one. Now, what about that one loop? Okay, this is one loop. Which loop? This is the IM1. Okay, E. So out of that calculation, we know this one. This is the IG squared. This is the IG squared and the IP squared. M is this M, okay? M is this M, okay? This M, the same M. Maybe let me put this in loop. A function of P, then IP squared. This is the complete result, right? You see, just following Feynman rules, okay? The two vertex, the two additional internal lines, okay? And then together with that loop calculation, that is the loop calculation. We already obtained the result. We just plug into here. So this will be equals to IG squared 1 over P squared minus G squared over 32 pi squared log minus P squared over lambda squared P squared. That's it. And in terms of Q, as said, in this case, minus P squared is positive. So we denote it as Q squared. So the total amplitude is given by sum over this two, right? By sum over two. So totally, the MQ equals to M0 cube plus M1 cube. This is equal to G squared over Q squared. 1 minus 1 over 32 pi squared G squared over Q squared log Q squared over lambda. Okay. Now we are ready to do the renormalization program, right? Because we finished the calculation. It's essentially, it contains two parts. First, you have to know how to deal with the integral. You have to compute the integral, loop integral. Once you finish the calculation of loop integral, or you can find an amplitude result, then you turn to this. This is basically you finish the mathematical procedure. Now you turn to the physical renormalization procedure. The renormalization procedure will avoid this cutoff. So in this case, since the dimension, if you count in the dimension is that the G is dimension 4. Okay? G is dimension 4. So you can redefine G squared over Q squared as another column. Okay? This is okay, right? This is okay because eventually we want to define some renormalize the coupling or physical observables. That physical observable must be measured at some energy scale, some Q scale. So your experimental friend know which Q they are working on. Okay, so it doesn't matter. You redefine your coupling or your coupling minus plus your coupling times some Q squared over some Q squared. This doesn't matter. This is definition. This is just a redefinition. You get an MQ. Squared minus plus. Now you turn to the same program for the renormalization program from this result. You can easily justify yourself. Easily justify yourself. For example, now start the program. Okay. Now start renormalization. For example, one can define the renormalized computer square as some amplitude, okay? Some amplitude and some Q0, okay? And Q0. You start to do the program. And then you solve it, okay? You solve this, from this condition, you solve this pair equal square in terms of renormalized. The sign changed, okay? Now you plug this into the original amplitude. Okay, the original amplitude, which is this, which is this one. Then what you get is the M curve in terms of GR tutor plus. Okay, so this is the final formula for the physical prediction, as you can see. Because we express the amplitude at an arbitrary scale Q or momentum Q in terms of the renormalized curve. Okay, there's no cutoff energy. Okay, cutoff drop. This is the same game what we did the phenomena before. Okay. Same game. So the reason we want to touch is the QED, right? So this 5-qubit theory, one loop calculation, and this renormalization program is prepared for really renormalize the QED. Okay, renormalize the QED. So the similar loop diagram in QED, analogous to this one, will be the one loop correction for the photon propagator. Okay. In QED, you have photon, you have electron, okay? You can talk about the loop correction for the electron propagator. You can also talk about the loop correction for the photon propagator, okay? So as you can imagine, in QED, there's a similar diagram which has a very clear physical meaning, okay? Like this diagram in QED, okay? Your electron scatter, they pass through and they exchange a photon, okay? And there is a photon propagator here. And then at one loop level, there is another loop correction for the photon propagator. And this is called the loop correction for Coulomb's force, okay? Which is very, very physical. So we should talk about this one. So let's turn to QED. But of course, as you can imagine, in QED, instead of scalars or bosons, they're fermions, okay? The fermion appears in this loop. So you have to deal with the integrals, not only like that, but also additionally with fermion or gamma matrix, okay? So there's a little more complication. So let's see. So let's move forward to QED. And again, talk about the first the loop collection for the propagator. Okay, for the propagator. Just like what we did in 5-qubit theory. Like this is P, this is P, and this is K, and this is K minus P. And so let's evaluate this diagram. So what is the result of this CKD? Let's do it. So we should have minus I e following our previous convention. This should be taken twice, okay? Square the two vertices. Okay? And there's a loop. There must be momentum integral. There's a loop. Inside the loop, there are two propagators, okay? the two propagators. But since this is QED, as we emphasized before, the propagator is the Dirac fermion propagator, and in particular the gamma matrix. You have to be careful. So why I call this P minus K? Even though they're the same. So maybe like this. And times a trace, okay? There's a loop, so there's a trace. Gamma mu A slash minus P slash plus M. Gamma nu K slash plus M. And then take trace. And then there's a decay. Okay. Okay. So there are two vertices with two gamma matrix. Okay. With two gamma matrix. With two gamma matrix. Now at this moment, as you can see, I didn't specify the photon polarization epsilon. Okay. Because later I will take use of this as a part of a larger diagram. I don't really directly compare this result with a single photon scattering, okay? That's not what I want. I want to insert eventually this wonderful result like what we did here before, okay? Into a T-channel diagram. That's what I eventually want to do. So for that reason, I didn't specify the photon polarization, okay? I just take this result as a propagator, as a photon propagator, okay? Is that okay? This is a wonderful bracket photon propagator. It can carry the index mu and the nu, right? So the right hand side you have a mu and nu without a contraction, okay? Without a contraction. So this is the result. So is this the final result? There's something we missed.
-1.
Okay, very good. There's a fermion loop, minus sign. Okay, don't forget. So there's an additional minus sign here because of the fermion loop. For each fermion loop, there's a minus sign. Okay. Then this is the result. So the leftover thing is just the calculation. Just do this calculation. Now you take use of the trace. You do using the trace formula. Okay. Use trace formula, you can calculate that one. Then find your trace. Find your trace is actually equal to unknown formula. This is your result of the trace calculation. Okay, the trace calculation. Now it said that later I will put this graph into a larger graph in the T channel with two external electron scattering. Okay, as we discussed before, so which means this is essentially the photon propagator result. In this photon propagator result, we already discussed before. The term proportional to P is trivial, right? Remember that? Because that's the gauge dependent term, right? We don't care. Those linear to the P term. So this is P nu term are trivial, okay? Remember that? Because whenever you insert a photon propagator in a scattering, with the own shell of external fermions, okay? this term in the photon propagator, which is proportional to P mu or P nu, is gone. It's vanished, contributed 0, right? Because the on-share condition. Remember that? Okay. Essentially, that term is together with 1 minus Kc. Okay. Kc is the gauge parameter. Okay. It's gauge fixed parameter. So that's the gauge dependent term. It should disappear. So you can safely throw away. So you can drop the P mu term. P mu term. Okay. Now you do the remaining integral. Again, you use Feynman trick. Let me go left. Then what you have is the 2k mu plus g mu over p minus k squared minus m. You use the same trick as before, okay? You use the same trick as before. It's just a little complicated, right? You see that? Previously, we don't have such kind of numerator in the scalar case, right? We know how to deal with that one, right? Without this part. Now you see in QED, the new ingredient is we have this numerator, right? Previously, we only have the denominator, right? With 2I here in the scalar case. But now we have a little more complicated structure here. Okay? So you have to deal with this integral. So how to do this integral? Yeah, similarly, you use the Feynman integral trick, and you shift the k. The k is the free momentum, which you integrate over. Then you can turn this integral to that. You similarly use this Feynman integral trick. And you shift the k. The shift does not change the integral. Then you get pi mu equals to 4 pi e to the square integral. This comes from the Feynman integral trick. Okay. Okay. We got this one. You get a square, basically. You get a square in this denominator, right? Which is what we want, okay? We want to turn that two piece in the integrand to a single square in the denominator. Okay, so this is the result. Now what you do? Still is a little complicated integral. Okay? In particular, there's a king here. Then you can justify. In order to do this, you can employ something we don't have time to discuss in detail, but it's a very powerful trick for the dimension. Use dimensional regularization to do the integral. Use the dimensional regularization, you can deal with this integral. So what is dimensional regularization? I mean, it's a little weird trick, but it's reasonable. What's the idea? The idea is as follows. As we saw previously, right? Somewhere here. Somewhere here. Somewhere here. Okay? Somewhere here. Let's turn to this example. So what is the idea of dimensional representation? The point is as follows. Now you are stick to calculate this integral with the 4 dimension, right? Okay? But you can relax a little bit. You can relax a little bit. You are supposed, you just pretend you are not doing this 4 dimension, but D dimension. Okay? And if you're lucky, for some particular D, or some set of numbers of D, you do know the integral. Okay? Okay? Then you can just continue, do the analytic continuation. Okay? You can continue this D to 4, to whatever you want. Okay? By just using this continue trick, you can get the final answer. That's another trick to do in. Is that clear? Is that clear? Because quite often, in general D dimensions, the integral result of this integral becomes some gamma function. Okay, and the gamma function have very nice analytic continuation. Okay, so you can continue this gamma function as a variable in terms of D, to D equals to 4 or 2 or 3 as you. Okay, that's the trick of the dimension regularization trick or dimension continuation trick to perform the integral.
Excuse me, the D here is the integral or a continuous variable.
Finally, continue the D. Continue this one. A good question. D is not if you just accept, say, I only accept the meaning of D equals to 2 or 3 or 4 or 5, then of course it's not a continuous variable, right? The point is, quite often you can think this is a continuous variable. Okay? Then you realize that the gamma function naturally continue together. You can check it, right? This is not inconsistent, right? It's not inconsistent. What I'm trying to say is, if you can express the general dimensional integral as a gamma function, which is as a variable as a D, you can check that there's a way to connect all these discrete point data. Okay? I mean, that gamma function continuation is perfectly consistent with the data for the equal to 2 or 3 or 4. Okay? Right? It's not inconsistent, right? For example, if you are a person, you don't accept that the dimension can be treated as the continuous variable, then you only agree there are point data. This is data for D equals to 2, this is data for D equals to 4, this is data for D equals to 3, something. But you find that there is a continuous function connected, okay, which is the gamma function, which is the gamma function. The gamma function is a very, very mysterious and powerful function in the regularization. In fact. Yeah, this story happens many times. For example, when you compute the Casimir energy, the similar story happens. Or ground state energy. Okay. You can use zeta function. Okay. You can use zeta function. For example, you want to compute 1 plus 2 plus 3 plus. Of course, if you naively do this sum, you achieve nowhere, right? Because it can never become a finite number. But if you use zeta function, it does the continuation, okay? Then you get a zeta function with the variable as the power, okay? Okay? Then you continue this variable to 1, okay? Then you find from the zeta function you get a number which is a minus 1/12. Okay? Okay? That's the magic of the function. But in this, we don't go that further. Right? In this integral game, it's much more straightforward. It's much more straightforward. And the point is, this continuation method, the result produced out of here is perfectly consistent with other methods. You can try to do the integral in different ways. So yeah, let's do the trick here. So what should I do? So pretend now instead of 4, now you do the d-dimensional integral, right? Then this is minus 4, right? E squared g mu nu integral 0 ds d k, okay, dk, the d 1 minus 2 over d 3 squared minus x m 1 minus x p squared m squared over k. Right? So from here to here, we also use some other identities. The identity, for example, we can safely you can safely replace this one to this one, and the integral does not change. The value of the integral does not change. Okay. You get this one. You get this one. Is that okay? I don't do anything. You see, I just change the 4 to d. Okay, just relax your dimensions. Okay. If I know how to do the d integral, of course, finally I set d equals to 4. I get the result. No. Okay, it's not a big deal, right? My original problem is to do the integral in the 4 dimensions. But suppose now I relax myself in any dimensions, okay? In any dimensions. If I know the result for any dimensions, of course I know the result for 4 dimensions, for sure, right? With any dimension, then eventually set d equals to 4. That's it. This is the step I go. Now you realize that by relax the dimension, then the total dimension of the integral changed. Okay. Okay. The total dimension of the integral changed. Why? Because here is previously 4. Counting dimension here previously is 4. Now it becomes d. Okay. You see, it becomes d. Other dimension does not change, but this entire dimension changed. They compensate with that dimension. You put some mu 4 minus here. When d equals to 4, it's gone. Okay, it's trivial. There's some auxiliary parameter mu or scale mu with the mass scale and with the power of 4 minus d. Okay, in order to make everything has the correct dimension. Okay, now the point is we do know. The point is we do know these two integrals in d dimension. Okay, as a mathematical result. We do know d equal to the d k squared minus delta as what we discussed there. We do know this result. This is minus d over 2 4 pi d over 2 1 over delta 1 minus d over 2 gamma function. We do know this result. Okay, we do know. We do know this result. Yeah, you can try to calculate this one or justify why this is correct. Okay. In terms of gamma functions, we also know with numerator is 1, what k squared? We also know this result. Also in terms of gamma functions. Okay, gamma functions. Now you realize, okay, if you know this, then you basically know the result, you know? Right? You basically know the result. No? First, I relax the d away from 4 to general d, okay? Then I claim for general d, I do know the result, okay? Then you eventually set d equals to 4. That's it, right? That's the game. And the integral here is only really about these two structures. One has a k squared, another does not have, okay? Right? So if you know these two pieces of integrals, then you put them together, you know how to do this k integral. Then eventually I set d equals to 4. Finished. Finished. Yeah, so let's complete this calculation. Let's complete it. So that delta equals to -4 equals to m squared minus t squared x. Okay. And this pi 2 mu equals to -8t squared t mu e squared over 4 e over 2. Mu minus t. And then we have dx x minus x. Delta. Okay. So yeah, so I plug into these two pieces of result. Eventually, I get this result. And the last step is just set d equal to 4 minus epsilon. Instead of just set d directly equals to 4, I set d equals to 4 minus epsilon. Why? Because if you directly set d equals to 4, the gamma function will blows up. Okay, they're also poles. Okay, it's not surprising, right? That's essentially we want to use this trick. There's no free lunch. Okay, there's no free lunch. So the payment here is I want to set this epsilon is very small, which means I want to set the dimension is very close to 4, but not really. Okay, very close to 4, but not really. But with an epsilon deviation. So if you do this and then you expand or set the epsilon goes to their limit, or do the expansion for small epsilon, you will get the result. Right? This is the result. This is the result.
Sorry, what's the log and tilde here?
You mean mu? This is mu. Sorry.
Oh.
Mu is proportional to up to some constant, which is not important. It's proportional to mu. The mu here. Okay. The numerical factor is mu. So mu tutor. So we observed some numerical factor inside the mu becomes mu tutor. Becomes mu tutor. Now, as before, finally the x integral you can perform directly. You can compute it. The x integral is computed directly.
Means 4 minus d.
For example, if I consider the q squared for q squared, which is equals to minus p squared, much bigger than m squared, I can ignore the m squared. Okay. So I get the pi 2 mu. After perform this x integral over there, I get the result. 2 over epsilon plus log mu tutor squared over q squared plus. Okay, so this is the result for q is much greater than m. Okay, you see, you get the result. You get the result, which is very good. Okay. Yeah, we're almost done, but last step we try to insert this one loop corrected photon propagator to complete real scattering amplitude. Okay. Insert this photon propagator to a scattering amplitude. So which scattering amplitude? Or which complete setup? So we want to, yeah. So we want to consider. We want to consider, yeah, as I said, we want to consider a diagram like this. Okay. Okay. The two electron with a change of photon, there's a one loop correction. Okay, the one loop correction. And as we know, the physics of this diagram is about the Coulomb force. Okay? This is the Coulomb force. This means in order to get the Coulomb potential in the momentum space, one can sum over the two. So one can have the momentum space in space. One can get the Coulomb potential. V is the minus I two. Okay. Because this pi two comes from here with the g mu nu factorized out with a p squared times g mu nu factorized out. Okay. So this part is pi two. So this part is pi two, and this one is the leading order because when you talk about the photon propagator, you have this diagram, you also have this. Okay. The pi two is only about this part. And eventually you will add these two, okay? Which means you add these two terms, okay? Then you treat the Coulomb potential as the diagram of exchange of photon propagator. You have additional two electron coupling. So you have E squared here, okay? You have E squared here. Now we already know without this one diagram, this is the single propagator result, which is the E squared over P squared. This is the momentum space. This is the momentum space Coulomb potential, okay? which you can work out in elastic field theory. Okay. This is E squared over P squared. Now the total calculation here is put the application of one loop correction here. Okay. One loop correction. Right. So this pi two is this one. Yeah, we don't have time to finish. Let me continue next time. Comes up, right? Okay. Let's continue next time.
看我的交流吧。就是它是地方，但是根据当前条件，那个是也挺热的，我考虑
这样一个。是这样的，那种假设度我们看
对的。
哦，2节，1节是那个实际上，
所以是必须 就让这个降到这样。
有讲究是
因为你如果是对递次的话，一定不能P是递次方 P 的话，这量大是不一样的。
质量才能划定
啊，那个
它的但是这个例子，那 P 方不是
意思就是说，
那 P 方是
我记得有那种，
然后我再这种
这个 P 是等于那个直线的
就是我们俩依赖
外径的这种少。
我们俩依赖点就是其实这个，我发现它其实应该还是为什么播放因为那个我们机制我们俩也是变成前那个我播放后来有
被 P 回来。
你这个播放你是在萝卜的后面拿这个播放点应该他什么那边对你的我们喊对，然后呢我应该还是现在上那个那个我前面播放不
有点到这一步在我这里可以是就是都是就是它 P 平方小于0大于
然后我记得我当时
那 C 发现会选择一个位置，amplitude
这个拨号我们还有一个。这个可以正一次我们俩也
可以是正的。你如果是正的的话，那比如说它放一个负的，那不是那我取哪个变数了？
其实我们俩也的意思像
啊 good，这个传承。
因为它是互相两个
对，
就是拨号3分0，那是它为什么这么样？
它是我和210是它的一个数，但是最后。
假如你就是你这个，假如这个拨号乘以这个我们俩也是我们接下来是西部高率，也就是一个处处都不一样。
是区间0.6。
虽然并不是因为我们俩也已经拨号或者多少个地方，因为这个萝卜可是也是这一点。
我的问题是我当时130。
好像不是这样的，是吧？
因为我的
方法定要这就是它的。
然后呢，我这块然后先发现。
对，但应该是 minimum 这个区域的这个 m 还是这个。那怎么挑一个值出来？这儿可能看不出来。你们为什么把 Q 叫做一个 physical score？
相当于
对对，它是叫 physical。啊，因为它就是 schedule 这个 Q 中的功能里的scale，就是说你在哪儿做实验，就 physical。那这个 scale 是什么？scale 是什么？scale 是
那个没有点。